Hello students, today we are going to discuss thermodynamics in physical chemistry chapter of class 11. Thermodynamics. It is the branch of chemistry that deals about energy changes in the chemical reaction. It deals about the energy changes during a chemical reaction. Now we are going to discuss some basic terms in the thermodynamics. First, some basic terms. The first one is system. The system is a part of the universe that is under observation for thermodynamical studies. The part of universe that kept under observation for thermodynamic studies. Now we are going to discuss about surroundings. 2. Surroundings. The part of universe other than the system is called surroundings. The part of universe other than the system is called surroundings. Now universe is the combination of system plus surroundings. Universe. Now we are going to discuss types of walls. There are two types of walls, rigid and imaginary. Types of walls. One is rigid and second one is imaginary. Now there are two types in rigid, that is movable and immovable. A. Movable. 2. B. Immovable, that means fixed. Now in imaginary there are two types. A. Adiabatic and B is diathermal. In adiabatic process, the heat is not exchanged with the surroundings. But in diathermal, the heat is exchanged with the surroundings. Now we are going to discuss the types of systems. Types of system. It is based on heat exchange. Based on exchange of heat and matter. There are three types. One is open system, second one is closed system, and third one is insulated system. Open system. It can exchange heat with the heat and matter with the surroundings. It can exchange both. Now, close. It can exchange matter. Now, insulated. It can't exchange the matter and energy with the surroundings. It can't exchange both with surroundings. Now we are going to discuss about extensive and intensive properties. Extensive and intensive properties. The properties that can depend on mass, concentration, temperature, and so on. The properties depends upon the concentration, color, quantity, etc. are extensive properties. Now we have 500 kg mass and 100 kg mass, and we have to compare which has more mass. Then we can preferably say 500 kg has more mass. Now we are going to the examples. Mass, volume, mole, etc. Now we are going to discuss about intensive properties. Intensive properties are opposite to extensive properties. The properties doesn't depend upon the concentration, color, quantity, etc. are called intensive properties. Example: pressure, temperature, density, etc. Now we are going to discuss about characteristics of extensive and intensive properties. Now, characteristics. First, to convert extensive to intensive properties, we have to divide by either mass, moles, or volume. To get intensive properties, the intensive properties are multiplied by, or students, it is divided by molar mass, molar volume, molar moles, etc. Let's see an example. Here the extensive property is mass, and we have to get density. Now we have to divide by molar volume. This is the density, we get density. This is an example. Now if we differentiate the extensive properties, with the time we get the intensive properties. We get intensive properties if we differentiate with time of extensive properties. Okay students, now we are going to discuss the state and path function. State function. The terms which depends only on the initial and final position but not the path traveled. Let us see by an example. First, suppose it is A, it is B. Now the terms which are depend only on A and B but not the path. That means if we go like this or like this or like this, it independent of the path but depends only on initial and final positions. The terms which depends only on initial and final states but not the path followed. As of this chapter, the state function is followed by only internal energy. Example, internal energy. Okay students, now we are going to discuss about path function. Path function. Now, the path function is a term which depends on the path traveled, but not on the initial and final positions. Let us see an example. It is reactants. Here are the reactants and here are the products. It does not depend upon the states, initial and final state, but depend upon the path followed. There is a straight line path, or there is a projectile motion, or there is a triangular motion, or there is a zigzag way. Now, let's write the definition. The terms which does not depend on state. Students, here state means initial and final. Initial and final, and depends only on path followed. Okay students, we have differentiated between state function and path function. Now we are going to discuss about heat capacity, molar heat capacity and their relationships. Okay students, have you covered it? Okay. Now we are going to discuss about heat capacity. Heat capacity is the term used to express the change in temperature for changing the unit mass of a substance. It is the term used for rising temperature by giving certain heat. Now, for 1 calorie heat, the capacity is Q. For delta T, sorry students, here there is a mistake. For 1 degree increase, the heat is delta Q. For delta T increase, the heat is delta Q upon delta T. This is known as specific heat. Yes, it is denoted by yes. Now we are going to discuss about more specific heat capacity. It is for the substance 1 kg mass or mkg mass. Specific heat capacity. The heat required for rising T temperature for m kg mass. It is denoted by small c, and it is expressed mathematically as delta Q upon mass m into delta T. Now we are going to discuss about molar heat capacity. It is for 1 mole or n moles. Molar heat capacity. The heat required for rising T temperature for n moles. It is denoted by capital C, and it is expressed mathematically as delta Q upon n delta T. Now we are going to discuss the relationships between these three. Heat capacity. As we have discussed earlier, heat capacity is equal to delta Q upon delta P, and specific heat capacity is equal to delta Q upon m delta T, and molar specific heat capacity is expressed as delta Q upon m into delta T, and we are going to discuss the relationships between these three terms. First, we are going to discuss between these two terms. It is denoted by S. Now here we can split it up as 1 by m into delta Q upon delta T. Here delta Q upon delta T can be replaced by S, so it is written as S by m. So it is equal to small c. Here it is the relationship. Now we are going to discuss the relationships between heat capacity and molar specific heat capacity. Now here it is written as delta Q by delta T into 1 upon n. Here we can write it delta Q upon delta T as S. So it is written as S by N is equal to C. Now we are going to derive relationships between this small c and capital C. As we all know that N is equal to small m by capital M. Now we can replace small m is in here. Now we can write here S by M is equal to C. In the place of S by N is equal to C, capital C. In the place of N, we can write as M by M. So M into S divided by M, it is equal to small c. As we have discussed now, it is S by M is equal to C. So capital C is equal to capital M into small c. This is the relationships between these three. Now we have two types of molar heat capacity. It is at constant pressure and constant volume. Constant pressure, it is denoted by Cp, and constant volume, denoted by Cv. Now there is a relationship between Cp and Cv in molar heat specific heat capacity and specific heat capacity, only specific heat capacity. Now let us write the relationships here. Cp minus Cv is equal to R, and small cp minus small cv is equal to small r. It is this both for 1 mole. It is for 1 mole, and it is for 1 kg mass. Okay students, now we are going to discuss degree of dissociation. Sorry students, degree of freedom. Degree of freedom states that in how many ways the system can attain energy. Degree of freedom, it denotes that how many ways the system can attain energy. In how many ways the system can attain energy. Now there is a relationship between Poisson's ratio and degree of freedom. It is denoted as F. Now there is a relationship as Poisson's ratio, gamma is equal to 1 plus 2 divided by F. And we have also a relationship between molar heat, constant pressure molar heat capacity, and constant volume molar heat capacity. Gamma is equal to Cp upon Cv. Now we are going to write up for monoatomic, diatomic and triatomic. First we are going to make a table. Serial number, atomicity, degree of freedom, and gamma and Cp, Cv. First one, this monoatomic, it is denoted by 5/3. It is 5r/3, no 5r/2 and 3r/2. It is 3. Now second, diatomic. It is 5. It is 7/5. It is 7r/5. So for instance, it is 7r/2 and 5r/2. Now triatomic. Triatomic has 6. It is 4/3 and 4r, 3r. It is the values. It is the values. Now we are going to discuss internal energy. Internal energy. It denotes all the types of energies in a system. Denotes all the types of energies present in a system. Now it is denoted as delta U. It cannot obtain individually. We can find the difference between final energy and initial energy. We can't obtain absolute values, but can obtain change. Now delta U can be represented as delta U is equal to U done by PV work plus U work by non-PV work. Here non-PV work represents gravitational energy, mechanical energy, electrical energy, nuclear energy, and so on. This electrical energy, gravitational energy, and nuclear energy, and so on. Okay, students. Now we are going to write the relationship. Delta U is equal to N into CV into delta T. It is applied for ideal gases at all conditions. Applied for ideal gases at all conditions. It is applied to non-ideal gases at constant volume and temperature. Applied at constant volume and temperature. Now, if CV is independent of temperature, now we are going to integrate this. Delta U is equal to integral of N into CV into delta T at T1 at T2. Here delta U is equal to integral n into Cv into delta T. Here T1 to T2. If Cv is independent of the temperature, if Cv is independent of the temperature, we can directly use this term. If Cv is used, if Cv is dependent on the temperature, we want to substitute the values and we want to integrate this term. Now we are going to discuss about heat. Heat is the mode of transfer of energy. Mode of transfer of energy. Now we have discussed about internal energy and heat, and it is denoted by Q. Now we are going to discuss the work done, and the last term is the thermodynamic process. Now work done. Now we know that work done formula is force into displacement. As we know that force is equal to pressure into area. It is dx, and area into dx represents volume. Work is equal to P into delta V. If external pressure is applied, if P is equal to P external, work is equal to minus P external into delta V. Now we have a formula for work done. Work is equal to minus n into Cv into delta T. It is applied at constant volume. For ideal gas, for not ideal gases, for ideal gases it is applied at all conditions. Ideal gases applied at all cases. 2. Applied at constant volume temperature for non-ideal gases. Now we have now work done is equal to work done by PV plus work done by non-PV. Now work done by PV means it is pressure and volume. If the pressure is increased, volume will decrease. Pressure increases. It is for work done. As from the Boyle's law, pressure is inversely proportional to volume. Okay students, now we are going to discuss the last topic, that is time convention in this session. Sign conventions. sign convention is necessary for using the thermodynamic equations. Now, heat is added. Heat is removed. If heat is added, it is considered as positive. If heat is removed, it is considered as negative. Work done by system. So it is taken as negative. Work done on the system. It is regarded as positive. Now, temperature is increased. Temperature increases. It is taken as positive. If temperature decrease, it is taken as negative. Now, if you use this all sign conventions nicely, you can get all the positive values. If you use opposite, we can get the errors. That's all for today, and in the next section we are going to discuss about laws of thermodynamics. Thank you, students.